let's do some integrals, multiple integrals. I'll go over some essential things in calculus 3. So the basic idea is that if we have in 3D in the xy plane, a domain D, let's say, this is the xy plane. And okay, we can consider like a cylinder, base is D, and then a continuous function which describes a surface in 3D which stays, let's say, above D. Doesn't have to be above D, but just for simplicity. So we have a surface. So let's see, it's something like this, and this surface goes like this. And this is a surface. If we have a point xy, which actually is xy and 0, z equals to 0 in the xy plane, but we can take it as an xy, and raise a perpendicular onto the xy plane for the point from this point, and it will intersect the surface of the point, which will be x, y, and f of x and y. On the graph of the surface, this is the surface z equals to f of x and y. Whenever we have a continuous function, the equation z equals to f of xy describes a surface in 3D, and the picture is kind of this one. So if this is the point xy, this is the altitude z, which will be f of x and y. And now, the double integral over the domain D of the continuous function f of xy dA is the volume of the solid in 3D, which is above the domain D and below the surface z equals to f of x and y. So the volume of this of the solid in 3D between the plane domain D and the surface z equals to f of x and y. Okay, so let's discuss some very simple cases. Example 1, let's say the domain D is any domain D, and then f of xy is a constant, let's say 1. Right? That's more simple than 1. So we get it's like we vertically translate D, lift it with a distance of 1. It's another copy of D, like a cylinder in 3D. There's the base, lower basis, upper basis. There's a copy of D, and let's say the distance between the lower basis and upper basis is 1. So what will be the double integral over D of 1 dA? Right? Because f of x and y in this case equals to 1, or z equals to 1 is the surface. Above D, so z equals to 1, but the fine print is z equals to 1 above D. So in that case, the double integral over D of 1 dA is the volume of the solid in the lower basis and upper basis. What is this? It's a cylinder. Everybody knows that the volume of the cylinder is area of the basis times height. Like, for example, the volume of the pyramid is area of the base times height divided by 3. But in this case, we have a cylinder, so this is the volume of the cylinder meaning that cylinder which is area of the basis, area of D, the basis being the domain D, times height. Height is 1, which will be area of D. So a very nice formula here, double integral over D of any plane domain D of dA equals to area of D. Okay, that's the substance of example 1, very easy example. Okay, let's do example 2. Based on this idea of volume, let's say D is the domain consisting of the points x, y in R squared. Vertical bar is with a property that let's say x squared plus y squared less than or equal to R squared. What is this? It's a disk centered at the origin with radius R. Right? So find the following. Find the double integral over D, square root of R squared minus x squared minus y squared dA. Based on this side, so it looks like a complicated integral at the first sight, but if we think of this integral like a volume formula for some volume, then it's very kind of trivial to do. Right? Okay, so as a volume, what do we have here? We have this domain, which is a disk centered at the origin of radius R. So this will be like, imagine this disk. So sometimes it's better if you don't really draw the coordinate axis, but imagine this is a disk D centered at the origin with radius R. And then, what is surface? This surface, look at this surface, is like this. Z equals to square root of R squared minus x squared minus y squared. And then if you square both sides, we get Z squared equals to R squared minus x squared minus y squared. Bring the negatives from right to left. X squared plus y squared plus z squared equals to R squared. What is this? It's a sphere centered at the origin of radius R. But z being a radical, z is positive because z is the radical of something. So then we have a half sphere. So the surface is a sphere which hemisphere above the disk centered at the origin with radius R. Now we can put a coordinate axis. So this is the z-axis, x-axis, y-axis. So what will be this triple integral? This double integral. Double integral over d square root of z square r square minus a square minus y square dA is the volume between the domain, which is the disk centered at the origin of radius R, and the hemisphere, which is the volume of the half the volume of the sphere, right? So again, let me do it more summarily. So this is the domain D, sphere centered at the origin of radius R, and then there's a surface Z equals to square root of R square minus A square minus Y square. That's a sphere centered at the origin with the radius R. Hemisphere, because this is Z, right? Z is positive, and then the double integral will be then the volume of the so 1/2 the volume of the solid sphere. 1/2 times 4 pi r cubed over 3, and that will be, after simplification, 2 pi r cubed over 3 is the formula for this integral. Okay, everything is nice and intuitive, but we need more than intuitive. We need some routine, some rules. So the first contact with rules is to do double integrals over rectangles. And here we get the idea of iterated integrals illustrated by the Fubini theorem. Fubini theorem. Okay, so now we want to do a double integral in which the domain over which we integrate is a rectangle. So say the domain D is the rectangle AB cross CD. So the understanding that the rectangle consists of, so D consists of all the points X, Y with a property, so vertical bar, X is between A and B, and Y is between C and D. So this will be the rectangle in the XY plane. For the Fubini theorem, we want to find a double integral over such a rectangle, D, of a function, let's assume it's continuous for simplicity, f of x and y, dA. What is dA? dA is the area element. Area element, imagine like an infinitesimal grain of area. So intuitively, in the xy plane, you can say this is x-axis, y-axis. If you take an infinitesimal variation of the x-coordinate and an infinitesimal variation of the y-coordinate, this will be small, tiny rectangle, infinitesimal rectangle. This will be dA, which will be dx times dy or dy times dx. So technically, it matters if we do first write dx and then dy or vice versa, because it has a role in the order of integration. So in any case, dA is the area element, which in rectangular coordinates is dx dy. So in this case, if we integrate a function over a rectangle, what we get? The plane is plane 1. So plane A, integrate x coordinate first, and then if we integrate the x coordinate, we get a function which depends on y, and then we integrate the y coordinate, we get a number. Or plane B, integrate the y coordinate first, we get a function which only depends on x, then at the end integrate the x coordinate, we get a number. So this will be two methods. First of all, we can do this, integral. Let's say integrate x coordinate first, so we have to do it so everything goes from inside out. First we do x coordinate, so integral from A to B should be the first which is done. Then integral from C to D is the last which is done. So the first variable we integrate is the x variable. That's why I do integral from A to B, f of xy dx. So in this part, we don't put a parenthesis. You don't have to put the parenthesis, but just for the teaching reasons. So if we integrate integral from A to B, f of xy dx, we integrate the x variable, and what's left is a function which only depends on y. So this one depends on y. Depends on y. Once we integrate the x variable, get a function which depends on y. We can integrate, because y is between C and D, right? Y is between C and D, we can integrate from C to D, whatever we get here which depends on y, dy, and get a number, right? Or we can do it differently. So this is, if you go this way, or we can integrate the y variable first and the x variable last. So integral, y variable first, integral from C to D first, f of x and y dy, and after we are done integrating the y variable, we get a function which depends on x, right? Once we get something which depends on x as a result of integrating the y variable, we simply integrate from A to B, whatever we got which depends on x, dx. And then an outcome of the Fubini theorem, and the Fubini theorem we said that the double integral is either this one or this one, in both cases are the same. And that's Fubini theorem. So Fubini theorem tells us how to integrate over rectangles. These are iterated integrals. Iterated means integrate first x and then the result will be a function of y, and then integrate y, get a number, or vice versa. Integrate y first, get a function which depends on x. The second step, integrate the x variable, we get a number. Both numbers are equal regardless of the order, and then the common value is the double integral over the domain D of the f of xy dA. Okay, this being said, let's do a complete example of Fubini. I got an example here. So the domain D, so say D is a rectangle 0, 1 cross 1, 3. 0, 1 cross 1, 3. And then f of x and y is 2x plus 6y. Now let's do, in the process, verify the Fubini theorem. We want to do double integral over D, 2x plus 6y dA. dA again being the area element. So this could be the first part. So integrate, let's integrate the x variable first, y variable second. Integral, x variable. So x lives here, and y lives here. So x is between 0 and 1, y between 1 and 3. So if we integrate the x variable first, integral from 0 to 1 on the inside, integral from 1 to 3 on the outside. So everything evolves from inside out. If we say integrate x variable first, we do integral from 0 to 1 first, we get like moving from inside out. Integral from 0 to 1 goes first, 2x plus 6y dx, right? And then dy, right? So if we do the inner part here, I'll not put that all the time the parentheses, but we understand in our mind to be a sort of parentheses here. So let's do the inside first. So everything, the word goes from inside out. So integral of 2x plus 6y dx is antiderivative with respect to x. When we do antiderivative with respect to x, y is treated as a constant. So we get x squared plus 6xy, right? Vertical bar between x equals to 0 and x equals to 1. The value when x equals to 3 is 0. So the value of x equals to 1 is 1 plus 6y. So this will be 1 plus 6y. So this will be integral from 1 to 3, 1 plus 6y dy, which will be y plus 3y, y plus y plus 3y squared, vertical bar from 1 to 3, right? Value of 3 is 3 plus 3 times 3 squared. 3 plus 27 is 30, minus value of 1 is 1 plus 3, which will be a 4. That will be a 26. So that's what we get if we integrate the x variable first and the y variable second. The same result, and that's Fubini theorem. If we integrate the y variable first, x variable second, with exactly the same number, and the common value, which is 26, will be exactly the double integral of the over the domain D of this function, 2x plus 6y dx. Okay, let's do the other way around. I need some more space here, like always, on this small board. So let me just to write down the okay, erase the word and just write down the number. You get a 26 here. So just for the record, just put here 26. On the other hand, OTOH, on the other hand, double integral over D, 2x plus 6y dA. So here, before we integrate x variable first, y second. Now let's integrate y first, x second. So integral, y first, 1 to 3 goes first, 0 to 1 goes second, 2x plus 6y dy and then dx. Okay, so we have to do this, the inner part first. The inner part will be 2xy, antiderivative with respect to y, 2xy plus 3y squared between y equals to 1 and y equals to 3. So again, let's calculate this exactly. So if y equals to 3, will be 6x plus 27, right? If y equals to 1 is minus 2x, okay, we can subtract the value 1. So minus 2x minus 3, which will be 4x plus 24. So we got integral from 0 to 1, 4x plus 24 dx. So that will be, antiderivative is 2x squared plus 24x from 0 to 1. Value of 1 is 26, value of 0 is 0. So we get again 26. So they control these two numbers, and the common equality with the double integral over the domain D 2x plus 6y dA is the essence of Fubini theorem. That's Fubini. Okay, so now we can calculate every integral if you want to consider. You can calculate every integral over a rectangle by using this method of iterated integrals. Some special case of very much interest is integrating separable function, which is a separable function means a function over a rectangle is a product of a function depends on x times a function which depends on y. So exercise 2, again, exercise 2 will get a bit more general. So we'll say V equals to AB cross CD. And the function f of x and y will be u of x times v of y. That's separable. Like in the case of differential equation, separable equation, dy over dx equals to a of x times b of y. So f of x and y equals to u of x times v of y, separable. So we don't need formula. If we do a double integral over rectangle, so AB cross CD, rectangle, of u of x times v of y, dA. So the double integral over separable function over the rectangle AB cross CD. That's the easiest possible case in which the calculus 3 reduces automatically to calculus 1. So this double integral is a product of two calculus 1 integrals. That means the x integral will be integral from a to b. So simply the x integral. So we only care about x here. Integral from a to b, because x varies from a to b. U of x, then dx. Dx is part of dA, because dA is dx dy. Times integral from c to d, the y part, v of y dy. And a very neat formula, right? And we call this formula SOR. SOR. Separable over rectangles. Very important. Tries to be a very useful because very effective calculus. Separable over rectangles. Right, so here is a concrete example. So very important. If we integrate over rectangle a separable function, this reduces the product of the x integral times the y integral. Right. Example 3. Let's do so. Calculate double integral over the integral z over the interval over the domain 0, 1 rectangle cross 0 pi over 2 x sines of y dA. So how to do this integral? So we get separable over rectangle as the motivation for what we are going to write. Is the x because it is separable over rectangles. X integral. X lives in the first factor, y lives in the second factor. Integral from 0 to 1 of x dx. Right? Then integral from 0 to pi over 2 of sine y dy. And that will be x squared over 2 from 0 to 1 is 1/2 times minus cos y from 0 to pi over 2, which will be 1 over 2 times 1. So minus cosine of pi over 2 is 0, minus cos 0 is 1. So that's the value of the integral, right? 1 over 2, okay, times 1. This is 1 integral. So that's a quick way to show how effective is this SOR, special case of Fubini. So SOR is a special case of Fubini in which the integrate over a rectangle of function which is separable, x times sin y. So like x times sin y is separable, x times y is separable, x plus y is not separable, xy plus x plus y is not separable, but if you add 1 is separable, so it's separable. Why separable? Because x plus 1 times y plus 1, but if you don't put this 1, it's not separable. In any case, SOR would be very good in plenty of cases later on. So far we discussed about integrals over rectangles. Let's move on and discuss about, let's change, so everything in mathematics we generalize, find more general cases. Let's change the domains. Let's say we want to integrate over domains which are more general than rectangles, right? So let's discuss. Integrals over domains of type 1. Integrals over domains of type 1. Well, type 1, I'd rather say simple with respect to the axis. No, sorry, with respect to x-axis. Simple with respect to the x-axis. So we get the domain D in this case is not a rectangle. So consists of all the points x, y, such that. So now, such a domain, x is between two fixed values. So x is between a and b. And for every x between a and b, y is between a lower function and an upper function. Lower function means low of x, and upper function I'll denote to be u of x. Lower, upper. So what's the geometry of the domain? How does it look like? X between a and b. So this is a, this is b, right? And y is between a lower function and an upper function. So this will be low of x, as in y equals to low of x, and this will be u of x, as in y equals to u of x. Upper, lower, upper, right? And there's the domain D. Domain of type 1 or domain simple with respect to the x-axis. So then, what will be a double integral over such a domain f of xy dA? Remember that the procedure always in the discussion of Fubini theorem was integrated from the inside out. So out being the last step of the calculation, which produces a number eventually. Now, in order to finally produce a number, the out part should terminate with an integral from a to b, so that we just produce a number. So this will be integral on the out will be from a to b. Why do we put out the integral on the left, integral from a to b? Because the work is from inside out. See, the work is from inside out. The last calculation will be an integral from a to b, which produces a number as it should, right? So integral from a to b, integral from log of x to u of x, f of x and y. First integral y variable, dy and then dx. So because x goes last, and because x is between a and b, so we do first this one. Again, we don't have to put a parenthesis, but I put it for didactical reasons. So this would be, if you integrate from log of x to u of x, f of x, y, dy, integrate the y variable, everything else depends on x, so this stuff depends on x. So Once we get something which depends on x on the inside, continue moving outwards. So integrate from a to b, something which depends on x dx. That will be a number, which number is double integral over d f of x y dx. So let's try to have an example of double integrals over domains of type 1. Let's say D is the following. Set of points xy with a property x is from 0 to 1 and y is from x squared to x. What does it look like? As the unit square, there's a point 0, 0, 1, 0, 1, 1, 0, 1. X is between 0 and 1, so we are only allowed to live in this vertical strip between x equals to 0 and x equals to 1. And y is between x squared and x. So lower function is x squared, lower. And upper function is x. So in this case, log of x is x squared, and u of x equals to x. Because between if x is between 0 and 1, x squared is less than or equal to x always. So we have to do, let's say we want double integral over d of, let's say, take a simple case, x dA. What will be this one? Well, let's see. Double integral over d of x dA. This will be, we need for last integral from 0 to 1. Integral from 0 to 1, integral from lower to upper, from x squared to x, x dy, and then dx. Right. So integral from 0 to 1, which will be the last calculation which points to a number. Then on the inside, integral from lower function, which is x squared, to upper function, which is x. The function we want to integrate, because we want to integrate x, the function, we integrate first the y variable, x dy we have here. After we are done, we get a function which only depends on x, and then we integrate from 0 to 1, get a number. Okay, so let's calculate each step. This one will be xy between y equals to x squared and y equals to x, right? Under derivative with respect to y of x is xy, and that will be integral from 0 to 1 of what? If y equals to x, we get x squared. If y equals to x squared, we get x times x squared is x cubed dA, and that will be x to the power 3 over 3 minus x to the power 4 over 4. Vertical bar from 0 to 1 is 1 over 3 minus 1 over 4 equals to 1 over 12. So that's the idea. So there are also domains of type 2, which is simple with respect to y-axis. So let me just state how they look like. The domains simple with WRT with respect to the y-axis of type 2. In this case, y is between c and d. So y is between two fixed values. Y is between c and d. And x is between, again, a lower function and upper function, but the lower and upper in this case depend on y. So x is between a low of y to u of y. So the lower envelope, to say, is x equals to low of y. The upper envelope is x equals to u of y. U upper, L low. So we get something like this, lower, upper. So in that direction is the positive y, x-axis is here, y-axis is here. So x equals to low of y in this one, x equals to low of y. And let's say this one is x equals to u of y. And that's the upper graph, lower graph, and everything in between is a domain D. Domain simple with respect to the z-axis, with the y-axis. So what will be the double integral over the domain of type 2, which is simple with respect to y-axis, double integral over d of f of x and y, any function dA, that will be, we leave the integral from c to d last. So integral, because c to d are, c and d are constants, and on the inside we have the integral from ln of y to u of y, f of x, y, dx. Once we integrate this one, we get a function which ultimately depends on y only. And then we proceed to the last step, we integrate the expression we got here in this parenthesis, which only depends on y, from c to d to get the number. So there's a formula for giving us integrals over domains simple with respect to y-axis.